So here we have c, that is the speed of light in vacuum. Suppose that c is unknown and we have some scientists that are trying to measure c. In fact, they're trying to estimate c2 here. In this famous Einsteinian equation, obviously E equals c2, mc2. So they have, through careful experimentations, the scientists now obtain different measures of C, and through x1, x2 up to xn, that has the following distribution, where the mean is c and the variance is sigma squared. So with these data, they're trying to find the best way to estimate C2. And then we're given that two natural ways of doing this is through the sample mean of all these estimates or measurements, and then square them all, or square them all first and then take the sample mean. That's the difference between T1 and T2. So first we're going to find the probability that T1 is always less than T2. And then we are asked to estimate the bias of these estimates. All right, so let's start with by 1. So the question is, what is the probability that T1 is strictly less than T2? What is this probability? In the hint here, we're given that we can start by comparing the two sums and see when they hold. So let's write T1 here as it's given, which is it's the sample mean squared, which is the same thing as the sum from I equals 1 up to n x I, and then we're going to square all these, and then we have, and the question is this, when is this less than, I'm going to write a question mark here, when is this less than the sample mean of the squares of these random variables, I1 to n, which is the same thing as T2 here. So one thing we can note is that these two quantities look awfully similar to the quantities that compose the variance. So what I mean is the variance of some random variable z is the same thing as the expectation squared, and this is just by definition, of the expectation of z, well, z2, 2 here. And this is, the variance is always strictly larger than 0 if we're dealing with a random variable that is a non-constant random variable, non-constant. In this setting, obviously all the x i's or the j's are they are non-constant. They're normal c sigma 2. So this will hold. And now by kicking this term to the other side, we'll see that we get that the expectation z squared is strictly less than the expectation of z squared. And that is in fact what these terms resemble here. So and this always holds. So it means that because these two terms are in fact identical to what we have here, this probability will always be 1. Moving on to do the second part of this question, we're now asked when is this, we're asked to find a bias of T1 and T2, and then basically that gives us information about what is the best way to measure this quantity C2 that these scientists are after. All right, so the bias here we're given of T1 is the same thing as the expectation of T1 minus the parameter of interest, which is C2. Okay, that's theta in this definition here of the bias. And T1 is just the sample mean squared, again by definition. Now, this is a bit of a complicated term if you start transforming this sample mean to the sum of all the variables here, like that. You could do that, and then just calculate all the covariances between the C's and see what that turns out to be. But that's awfully complicated. So we're going to use use a shortcut, which is that we will have to find the parameters of this sample mean. So what is the expectation of this sum? Well, that is the expectation over the sample mean I to n, I starting from 1 to n of the j's. Now, if we back a little bit and say, like, why do we do this? Why do we want to do this? Well, what we could do if we knew the sample mean and the variance, we could then use the reverse relationship, or basically this thing that we have here, and figure out what this term is here. And for that we need to estimate the sample, calculate the sample mean and the variance, so that we can see what this term here is. Okay, so the variance now. So let me just complete the calculation of this thing here, which is now we can take out the constant, we can pull in by linearity of expectations xj from 1 to n, and these terms we know are C from the information given in the problem here. And then we have n of those, so we have 1 over n, n of C, and then the n's cancel, and we're left with C. Okay, so that's all good. Now, what is the variance of this whole thing? Well, the variance is going to expand out this in the same way what the sample mean is, and that's x j 1 to n. Just be very careful here, and then taking out a constant here, we square it, then we can pull in the variance in the same way as we did for the expectation, j1 to n, And now the variances of these xj's are the same information given here, r sigma squared. And so we have 1n squared, and we have n of those sigma squared. And so the variance is sigma squared n. Okay, so we almost, well, now we have all the information we need to figure out what the expectation over x2 squared is. And for that we do the following, which is the variance of x, the sample mean is the same thing as the expectation over x2, the sample mean, minus the expectation of the sample mean squared. And now we know, now we just calculated what this is. This is C2 to C2, and this we don't know yet. This we know is square root to n. And so now we know that by just simple manipulations here, the same thing as squared n plus c2. There we go. Now we have what we need is that we just take these two terms and put it in here. And so here we have that this is squared n plus c2 minus c2. This whole thing evaluates to sigma squared n. That is the bias of T1. Now let's compare it to the bias of T2. Starting off with the same thing, the expectation of T2 minus C2, and the and T2 was by definition the sample mean of this squared thingy here. Actually, I see one little error here. This should be an n, just to be clear. Okay, so we have 1 over n sample mean x squared I, and then we have I going from 1 to n minus c2. We can, by linearity, pull in and pull out the constant from the expectation. So we have expectation over x2 I minus c2. This goes I 1 to n. And now we do the same, we use the same trick to figure out what this term is. Let's do it here. So the variance of xi, any of those variables, is the same as the expectation x squared I minus expectation xi squared. Okay, and again here we know by what is given to us from this problem that the mean is c and the variance is sigma squared. So the variance is sigma squared. Sigma squared. Expectation x2i minus, and here we have c2. Okay, so we pull it in, and this whole thing. Let's do the final step just to show that we have C2 minus should be plus, like that. Okay. So we have 1 n, we have n of those right? The sum is going from 1 to n, and all of these i's are the same. Squared n, squared sigma, and c2 minus c2, and the n's cancel here, and the c's will cancel when we open up the parentheses, and we end up with sigma squared. And we see that the bias of T2 is sigma squared, and this term doesn't depend on n. So that we will always, no matter how large, how many measurements the scientists make, they will always have a bias of sigma squared. Whereas here, if they use this measure, the T1 measurement, as n becomes large, the bias disappears. So the conclusion is it's better to use this way of measuring C than using that way of measuring C. Now, imagine that you would not figure out what this term is here by using this little trick, using the variance. You would expand out this whole thing. How would you go about doing that? Would you end up with the same thing? Well, surely you would, but how would you derive that sigma squared n? So let's think about this problem a little bit. It's a fun little exercise. So I'm going to copy this whole thing. I'm going to move down, and then I'm going to just move down this whole thing and see if we can arrive to the same conclusion. So let's just remove this a little bit here. Okay, so let's do the before actually doing the expectation, I'm just going to focus on this inner term here. Okay, so this inner term, I'm going to start here, is, as I said before, in the as defined. So it's the expectation. It's the sum. Sorry, it's the sum from I1 to n, and then we're going to square it. And this you can think of having x1 plus all the way down to xn, x1 plus all the way down to xn, right? That's the square, and you would then multiply out this, multiply x1 by x1 and so on and so forth. And that's a complicated term that will give us essentially by the binomial theorem how many pairs, well, let's start with how many squares do we get, unique squares. We get all the squares, the following for the following terms up to let's do the following plus x2n, right? We will get those unique ones, but we get a bunch of pairs of plus a bunch of pairs of the form of xi, xj, right? But how many do we get of those? We can think about them getting, well, by the binomial theorem, we get n choose 2 pairs, right? We can think of that we have n of those x's, and then we are pairing them together in the following way, and that's the same thing as n minus 1 2 factorial. Well, that's just 2. Those are the number of pairs that we get. So let me just remove or make a little space here, and then add, instead of this question mark, we observation. Okay, so that's all good. And now by putting this whole thing over an expectation, so we're going to now use the linearity of expectation here over all these terms. And what we get is expectation over x2, 1, and we get, in fact, actually, let's just do this, and we get n of those. And we're going to then do plus n minus 1, 2, and do the expectation over xi xj, meaning that these are all the x's that all x pairs that we have in this set. And just keep it like that. Then we're going to ask ourselves, what is the, and now we see the benefit of this approach is that we don't have to calculate the mean and the variance of the sample mean, but it leads to this sort of complicated little detour. But it's good exercise to do it. So, and we know that there are several things happening now. We're going to use the same fact as we used before. So this thing here is the variance of any I xi squared minus to the xi squared. This is the side, so I'm going to just move it like this. And we know that the variance is sigma squared. We also know that this is C2 for all of these terms. So we end up with the following. Now we have n of these squared plus C2. And now what do we do? And we still have this n minus 1, 2. What do we do with, right, we shouldn't forget the minus C2 here, right? Minus C2 here from this expression. So what do we do with the, well, by independence, so we ask, well, what we have an expectation of two random variables. Because these are independent, we can take the expectation of each of those separately. Just going to move this little j minus C2, but the expectation of each of those are C, right? That's C, that's C. So this gives us now n squared plus C2 plus n, and let's see, where are we now? n minus 1 C2 we have divided by 2. Now we have minus C2. Okay, so there's some way to go here to hold this expression comparable to this guy over there. All right, so let's see what we can do here. I'm just going to just thinking about this little problem here, where I think I have a 2 missing somewhere. Right, so let's see, we have the following. This looks correct. This looks correct too. Right, so now I see what I'm doing wrong here. So actually these covariance terms, we will have, so up here, these covariance terms here, let me just remove this a little bit. It's not just xj, it's two of these, right? This is the format of when you expand it out, but we have this many pairs of these guys. So this will mean then we're doing the expectation over, there's a 2 here, we take out the 2 there, and then now we can remove the 2, we'll cancel it out, so we end up having the following expression. Alright, so now we can, what do we do now? Well, now we try to put all these let's see, we have n of x and then bias there minus c2, and we have indeed right, so we have, I'm sorry about that, I'm forgetting the end here as well. So we have, after taking out the n from that parentheses, we have n squared there. So yeah, this is a little complicated way, but I think it's useful to see how it's different. So let me just move this a little bit to the side, and then what we have here, in fact, is that we have a outer parentheses that covers this part. And this says n squared, n squared, n squared, and now we end up having sigma plus c2 n, where the n, these two n's cancel, and then we have plus, and there's another n canceling here and there, n minus 1, like this, and then we have the minus c2, we're going to write it on its own n, like that, and now we have, the C2 shouldn't be forgotten here, otherwise we end up thinking about what just happened. Alright, so now we have this whole expression divided by n, and we see that the n's, the C2s, so we have, let's see, we have n minus, right, we can, right, so we have n plus that, we can add this whole thing here. This whole thing here is nc2, right? We have, because we have n minus c plus c2, so there's now n c2s. You can just see it like factorizing out 1 plus n minus 1. That's just n minus c to n. Well, that now just becomes squared n, which is exactly what this term here is. Let me remove this from the other calculation. It was a little involved, I admit. I even made some mistakes on the way, but found them. but this is another way of thinking about it without having to calculate the distribution or of the sample mean.